Okay, welcome back. Here we are for lesson 16.3. So for lesson 16.3, we're going to continue looking at exponential models. That is, again, functions that map the growth or decay of a quantity over time. But now we're going to look at fitting a model to data, which we'll talk about in a moment. So we're looking at 16.3 using exponential regression models, and our objective is to understand the strengths and the weaknesses of fitting exponential functions to sets of data. So in this section, we're going to do some investigating on what it looks like to write a function that fits a pre-existing set of data. So we'll have some points, and we'll see if we can make a curve come very close to it, and then we'll see how well that curve maps that data. Okay, so we want you to understand the strengths and weaknesses of this method. And just a couple of recall items. One, again, recall that an exponential function is a geometric sequence with domain all real numbers. So again, when we first encountered geometric sequences, our inputs were just integers starting at 1 because our input was a position within the sequence. And so we'd say, here's the position in the sequence, here's the term value, that was the output. Now we're using the same properties of geometric sequences where you multiply by a ratio to move along the function. But now our domain, our inputs, are not just integers starting at 1, but is any real number, positive or negative, integer or not. Okay, so that's what an exponential function is, and you know it's an exponential function when you see it in function notation because the x is in the exponent. The input value, the x, is in the exponent. Also recall that this is from the last lesson, 16.2. An exponential model shows how a quantity grows or decays over time. An exponential model shows how a quantity grows or decays over time. So we have an input of time and an output of some quantity or amount or number of a thing. Okay? So that's what we're dealing with today. So the thing is, in the real world, right, data doesn't always perfectly fit a function rule, right? So we have some function rule like y equals ab to the x, or when it's an exponential model, we were using the form y equals a times 1 plus r to the t, right? So the problem is, though, like, let's say that rabbits reproduce at a rate of, they double every 6 months, right? Well, it's not going to be a perfect factor of 2 every 6 months. So like maybe in the first 6 months, the population of bunnies doubles. But in the next 6 months, it goes up by a factor of 1.89. And then the next 6 months, it goes up by a factor of 2.15. And the next 6 months, it goes up by a factor of 1.7, right? And so it's above or below, but it hangs around 2 in the real world. So what we have to do is say, well, you know what? I can't map that real data exactly, but I can write this function that comes really close. And so in that case, with the reproduction of bunnies, we'd say that the ratio, the rate of increase is a factor of 2. And so even though it's not perfect, it's close enough, and it can allow us to make predictions out into the future of what that bunny population is going to look like. So the way that we take a set of data, so like if we took measurements of that bunny population over 2 years, we'd have some data points, and we'd say at time 0, their population was this, at time 6 months, it was this, at time 12 months, their population was this, at time 18 months, their population was this, at time 2 years, their population was this. And so we'd have data points, inputs of time, outputs of number of bunnies. And if we wanted to write an exponential model that fit that data, we would do what's called an exponential regression. Okay? And this is an operation that's usually performed by a computer or on a graphing calculator, and you type in all the data and you hit a key and it spits out a function. Okay? Well, in Algebra 1, we don't usually use graphing calculators, and I want you to kind of work with the data. So I'm going to teach you a different method today, and my method will be less precise, but it will give you the same idea, okay? So we're not relying on the functions we're writing to make strong predictions for the future. We just want to understand the strengths and weaknesses of fitting a function to data. So I'm going to show you a way to approximate fitting a function to data. It's not a regression. Know that a regression is something that a computer does. We are going to use paper and pencil to generate some functions that should come close to the data we're given. Okay? But I'm going to use an example on page 765 and 766 from your book. And that example will deal with is dealing with numbers of millions of internet hosts in the world starting in the year 2001. Okay, so the table looks like this, and it's X is years since 2001, and then Y is the number of internet hosts. And so this is data that's collected. This is real world data, and so it goes like 0, 1, 2, 3, 4, 5, 6. Okay, so we'll look at the first 6 years after 2001. It goes 110, 147, 172. 110, 147, 172, and that's millions of internet hosts in the world. 233, 318, and 395. 233, 318, and 395 and 433. Okay, so this is actual data that was collected. So they at that time in the year 2001 there were 110 million. In the year 2002, 1 year after 2001, there was 147 million internet hosts. 2 years after, in the year 2003, there were 172 million internet hosts. Okay, so that's how the data actually progressed. Well, we want to make a prediction and say, well, how about in 10 years, or in 20 years, or in 30 years, if it stays at this geometric progression, at this exponential progression, how many internet hosts will there be in the future? And so we're going to write a function that we can graph, and it will go out beyond 6 years after 2001. And so we'll be able to look out beyond 6 years after 2001 to figure out how many internet hosts there should be. Okay? So if you used a computer or a calculator to perform an exponential regression on this, it would spit out this function. It would spit out the function 113 times 1.27 to the x. Okay? Yeah. Okay, so it's saying that the y-intercept, the value at time 0 should be 113 million, and then it goes up by a rate of 0.27 every year. Okay, so and that's a curve that won't be perfect, but it will be close. Okay, so it ends up looking something like this. It's like, so if I have data points like this, right, my curve might go through here like that. So it doesn't hit all the points perfectly, but it comes close. Okay, and I know some of this is small. Remember, on YouTube, you can zoom in to see what I'm drawing. So again, we've got data points that are real-life data points. We form a curve that might not be perfect, but it comes pretty darn close. Okay, so if we were to generate values using this function, okay, they would be 113. This is predicted y. The predicted y. 113, 143, 182. $231, $294. $373, $474. Okay. So now we're saying, okay, these are actual values. In our model, our exponential model that shows the growth of this quantity over time, these are the values that we would expect based on our model. These are the values we would expect based on this model. Again, these data points are not generated by a function. They're just generated by life. They're just generated by how the world has grown and how the internet has grown. So these are real-world statistics. These are predicted by this function. Okay? And it should come pretty close to the data points. So if we want to measure how well a regression fits a set of data, we look for what's called a residual. And this is the distance between the actual values and the predicted values. Okay? This is the distance between the actual values and the predicted values. So we do this by saying we subtract the predicted value from the actual value. Okay? So we subtract this one from that one. So our residuals, okay, would be right here. It would be 110 minus 113 equals -3. That would be our residual right there for that data point. Our residual here would be 147 minus 143 equals 4. Okay. Our residual here would be 172 minus 182 equals -10. 233 minus 231 equals -2. 318 minus 294 equals 24. 395 minus 373 equals 22. And 433 minus 474 equals -41. Okay? So what we can see is, what you can notice is that in the beginning, the values are very close. So the difference between the actual data point and the predicted data point is -3, 4, -10, -2. But once we get further out, it doesn't stick with the actual values as well. It's off by 24, off by 22, off by -41. So the further out it gets, the less accurate the model is. Okay? So that would be if we had generated this punching it into a calculator or a computer. Okay? So that's all the vocabulary we have is like we get a model of, this is data, we get a model, that model gives us predicted values, we compare the data and the predicted values to get a residual, and the residuals tell us how accurate the model is. Okay? So now, real quickly, I want to show you, using some data in your book on page 769. I'll use some data that was given on page 769 to show you how I want you to do your exercises for this lesson. Okay? So now I'm going to show you what I'm calling Hoyer's method. Okay? So I made this up, but again, so that we don't have to use a computer or a graphing calculator, we can kind of guess at an exponential model for a set of data. Okay? So we're looking at number 9 on page 769. It says that there's a table that shows the population of box turtles in a Tennessee wildlife park over a period of 5 years. Okay? So they gave us data about how many box turtles were living in a particular park over a period of 5 years. So we have, year, that's our x. And we have population, that's our y. Okay? And so we have year 1, 2, 3, 4, and 5. Okay? And the population in year 1 was 21. The population in year 2 was 27. The population in year 3 was 33. The population in year 4 was 41. And the population in year 5 was 48. Okay? Now, again, we need a way to guess at a function that will fit this data. And remember, an exponential growth or decay is like a geometric sequence. So what we're looking for is a particular ratio from here to here, from here to here, from here to here. And if we were told that this was definitely an exponential progression, definitely exponential growth, that there was actually an exponential model that would fit it exactly, that would mean that the rate from here to here, here to here, here to here should all be the same. Okay? And that would be if all the data was exactly perfect, fitting an exponential model perfectly. But since it's real-world data, it won't fit perfectly to an exponential function. So what we have to do is come up with an r that's good enough. Okay? So in Hoyer's method, what you do is you find the rate from here to here, the rate from here to here, and the rate from here to here. The first three pairs. And you average those rates. Then you use that rate to build your function. Okay? So I'll show you. So first of all, we'll go from here to here. So what was we want to find the rate of change from the first point to the second point. Okay? So you should recall from previous work that rate of change is taking the second value minus the first value and dividing by the first value. Okay? So that's 6 divided by 21. That is rounding to the nearest tenths, hundredths, thousands. That's 0.286. Okay? And you would use your calculator for that. And make sure that you are performing the subtraction before the division. Or if you're putting it in your calculator, you can put the top in parentheses and then divide by the bottom. Okay. The next data point would be 33 minus 27 divided by 27. And that is approximately 0.222. Okay. Then finally we have 41 minus 33 over 33. Okay. That is approximately 0.242. Okay. Now, so that's the rate of change from here to here, the rate of change from here to here, and the rate of change from here to here. And again, we want one number. Notice all three of those are different because this isn't perfect data. Okay? But we want one number that can be our rate of change for the whole thing. So we're going to take these three rates and average them. Okay? So if I add them up, I would go 0.286 plus 0.222 plus 0.242. And I would divide that by 3 to find the average. That average is 0.25. Okay? That equals R. So that is going to be our rate for our exponential model. Okay? 0.25. So I'm going to erase this now because I need to do a little more work here in just a second. So R equals 0.25. Now, we need one other piece of information to write our function. Remember that an exponential model is y equals a times, and this is a growth because the numbers go up. So our growth model is 1 plus r to the t. And t is our input, so that will change, but we need a and we need r. We have r, we now need a. And remember that a is f of 0. It's the y-intercept. Okay? So that was not given to us. So using our r, we're going to generate f of 0. Okay? Well, f of 0 equals f of 1 divided by r. Because to get to this point, I had to start at the point before it and multiply by the ratio. Okay? So in this case, f of 1 is 21. So f of 0 equals 21 divided by 0.25. Or, sorry. 1 plus r, okay? Because to get from f of 0 to f of 1, I multiplied by 1 plus r, because if I went up by 25% of f of 0, then this value is 1 plus 25% of f of 0. So I'm going to divide 21 by 1.25. Okay? So 21 divided by 1.25 is 16.8. That's my A. So again, all you're doing is looking at this form, okay, and starting at f of 1 and going backwards to find your A. So my model for this set of data will be y equals 16.8 times 1.25 to the t. Okay? So let's see what values that generates. So if I use this model, then my predicted population of box turtles, now this column will be predicted population, That is 21, because I forced it to equal that. Okay. Then it's 26.25. Then it's 32.81. Then it's 41.02. Then it's 51.27. Okay. So now we can generate residuals to see how well our model does fitting the data, right? We can generate, we can find the residuals to see how well our model does fitting the data. Well, because we forced it to, the first one's perfect, so that's 0. Okay? The residual for the next one is 0.75, right? So we go population minus prediction, 0.75, right? Then for the next one, we go population minus prediction is 0.19. Okay? Then for the next one, population minus prediction, negative 0.02. Then population minus prediction is negative 3.27. Okay? So again, you can see that it might start to be more divergent. The data and the function might start to be more divergent the further out we get. Okay? So what we're starting to see is, yes, we can write functions that come very close to data, but they'll never be perfect if it's real-world data. The functions will very rarely be perfect. Okay? So that's what I want you to do on your exercises. You're going to have sets of data, and I want you to build these tables showing your work along the way. You need to be able to write the exponential model and build out the table that has the actual data, the predicted values, and the residuals. Okay? And you'll need to show your work for how you generated the exponential model. Okay? So have fun with that. Happy mathing.